Okay, so we'll start with electrostatics, and our first chapter will be charges and electric field. Bit of basics let us learn first, then let us go and take the topic. So the first chapter and second chapter, they are classified under electrostatics. Electrostatics deals with study of charges at rest, right? And in grade 10 you had heard about current is the flow of charges. You had read current I is equal to Q upon T is the flow of charges. That means in this chapter, in this particular chapter, some basics, you will not hear anything about current. Why? Because your charges are at rest. Come to chapter number 3. When we come to chapter 3, this will be in chapter 1 and chapter 2. When we come to chapter 3, we will have a charge, and this charge will move with what is known as uniform velocity or uniform speed. That means the acceleration in the charge will be 0, right? As a result of which you will get what is known as current. So that's why the first chapter is all about current. And this will continue like alternating current and all. And then when you go to the last chapter of this book or the first chapter of the next book, at that time the same charge will actually be accelerated. That's what you do in a microwave oven. So you will get what are known as waves. So this is how you study. You will be getting waves out there. Okay? So our study in these first two chapters will be all about charges at rest. And once a charge is at rest, that means the charge is not moving. It is stationary. It is a sort of static environment. And that's why it's called electrostatics. So all things that can happen with charges at rest. Okay. So building up a little bit of concept for this chapter and getting into the first topic of charge. So if you look at matter, so matter is composed of finally what? Atom. And when you get inside the atom, you get three sorts of particles: the electron, the proton, and the neutron, right? While neutron as set is not assigned no charge, it's an uncharged particle. The electron is assigned with a negative charge and the proton is assigned with a positive charge. Means there are two charged entities which are there in matter, and all matter is composed of atoms. So whatever matter you see in the universe, all these matter will have some sort of charge entity associated with them, primarily due to the electrons and due to the protons. Now some hypothetical studies. Okay, let's go back to grade. Let's take one electron and let's take one more electron. Okay, few things which you should know, like charge of an electron. Slowly we will study charge of an electron. The charge of an electron is said to be 1.6 into 10 to the power minus 19 coulomb. Now when I say charge of an electron, you might be in doubt, sir, why is it minus or it is plus? That's the polarity of the charge. 1.6 into 10 to the power minus 19 coulomb is the magnitude of the charge, right? Magnitude of the charge. And then we will assign a polarity, whether it should be plus or it should be minus. Similarly, we should also know mass of an electron. An electron is a very light particle. It's around 9.1 into 10 to the power minus 31 kg. And the mass of a proton, I may not remember so much, is around 1.6 into 10 to the power minus 27 kg. Right. A proton is much more a heavier particle. This is all you have studied in grade 9, that the mass of the atom is attributed to the proton because the protons are in the nucleus. Now, let's see some what do you call hypothetical studies. Okay, now if you take an electron and say you have done some spacing between them. Okay, I have done some spacing between them. Let's say it be 1 centimeter or 1 meter, roughly 1 centimeter or 1 meter. Then by my knowledge of grade 9, I know that electron has a mass. This electron has a mass. Every body in this universe attracts every other body with a force which is directly proportional to the product of their masses, inversely proportional to the square of the distance between them. Okay, so let's say that there is some distance and we'd be able to carry out, and that force is known as the gravitational force. So we will say that force will be equal to something like G, mass of the electron, into another mass of the electron divided by whatever is your R. I have taken R as 1, but we'll say R is the, let's keep it, instead of, let's keep it generic. Let's say this is R. square. Do you get it? That means, and we will get a value for this. I'm not concentrating on the value. We will get a value for this, which will be very small, but yet there is a value. That means we get to know one thing, that an electron attracts an electron based on the knowledge that we have so far, right? Based on the knowledge that we have so far, an electron attracts an electron, and mind my words, huh? I'm saying something which is controversial. An electron attracts an electron with a force which is defined by the gravitational force, because these two bodies have mass associated with them. However, the attraction is very small. Now, when we again take these two electrons and try to see, we also see that two electrons. So here we see that there is a attraction. Again, if we take an electron and we take an electron and we have the same spacing, okay, the same spacing r between them, then we also will see that there is a force of repulsion. Understood? While the attraction is attributed to the gravitational force, the repulsion is attributed to the electrostatic force between them. And if you, since you have studied this chapter, you know that if there are two electrons, then I would say that it is around 1 by 4 pi epsilon naught. Don't break your head right now into all this. Electrons charge into electrons charge divided by square of the distance. This is called the inverse square law in physics. Look at the two formulas. They are exactly same. Some constant into product of the masses divided by square of the distance. Some constant product of the charges divided by square of the distance between them. However, the FEL was found substantially large than the FG. So don't just say, like you used to study in kiddo classes, saying that, you know, electron will always repel electron. Electron attracts electron also. And you know the concept of net force. Since the electric force is much, much higher, so it is taken as the repulsive force is more dominant in this case, right? Now, can I go ahead? Okay. So the study further tells me that we did see something called a gravitational force. We saw a gravitational force, and we said that this gravitational force is Fg. The gravitational force is attributed to mass, whereas the electrostatic force, which was found, the repulsive force, now this force has to be attributed to some quantity, and that quantity of matter is called charge. So matter has some fundamental properties in it. Matter will have mass associated with it. Matter will also have charge associated with it. Overall charge may be zero, or there may be a net charge, but there will be a charge associated, and that is what is causing repulsion, right? After that, the same story was repeated, say, with one proton and one proton, okay? Between a proton and a proton, you again found that there is a gravitational force. Now, since the proton's mass is higher than the electron, the attractive force between the two protons, will be more than the, see, these are some entrance level question if they ask you. Attraction force between two protons will be always more than the attraction force between two electrons, because the protons are much more heavier, right? However, if you just try to see what is the electrostatic force between these two, this electrostatic force between two protons is exactly same as the electrostatic force between two electrons, and they are repulsive. Which makes us again understand that since the electrostatic force is attributed only to charges, understanding, right, are attributed only to charges, and mass plays no role in them, because the electrostatic force is fundamentally due to the charge property, and we found that the electrostatic force between two protons and the electrostatic force between two electrons, which are all repulsive, and they are equal, which gives us another identity, that the charge's magnitude on an electron must be equal to the magnitude, okay, of charge on a proton. Is this understood? Because you're finding the repulsive force same in both cases. The mass has no role, right? Between you two and say between two other children, we find the same repulsive force, and that is the electrostatic force. So that means the charge content between in one entity of you and in one entity of them must be the same, right? Then more iterations was done. Let's say a proton was taken and one electron was taken. A proton was taken and one electron was taken. And okay, sorry, children, I think this sign went wrong. A proton was taken, this will be in this manner. A proton was taken and an electron was taken, same separation. This time the electrostatic force that you found, right, between the electrostatic force between an electron and a proton, magnitude wise is same as the electrostatic force between what, a proton and a proton, or is same as the electrostatic force between electron and electron. But this is the first time that you are seeing an attractive force. Now, are you getting the ideas? First time we took electron, we found a repulsive force. Then we took a proton, we found a repulsive force. However, the magnitudes are same. That means the charge on an electron, I still don't know anything about the sign, Zoe. I just know one thing, that the magnitude of charge on an electron, and think that you have zero knowledge. We have no knowledge now, we are just testing. The magnitude of charge on an electron is same as the magnitude of a charge on a proton. This is established. No queries at this stage. After that, I did a test with a proton and an electron. I found the magnitude of the electrostatic force is same as that between proton-proton, same as that between electron-electron. However, this time was the first time where we saw the attractive nature, which makes us now conclude another thing, and that another thing that is that the polarity of charges on an electron and proton must be opposite. This is how human being is arbitrarily assigning. See, nobody knows who is plus or who is minus. Try to get the logic that if you are seeing an attractive force, why this attraction happened whereas the magnitude of charge was same. Then I say, look, the magnitude of charge on this and this are same, but the nature is not same, right? While the magnitude is same, we would say the nature is different. Now, as students of science, we are supposed to assign, a measurement value with every finding of ours. We can't go with a subjective statement saying nature is different. So we say the polarity of the charge must be different in these two entities. Have you understood? Story clear ho raha hai abhi dheere dheere? Okay. So let's take one more iteration. After that, see, this is the hunger. You took a neutron and you took another neutron, right? And you kept the same distance, and you found that between neutron and neutron, you found that there is always an attractive force. Between proton-proton also there will be attractive force, no doubt about that, but this will be less and this will be more. Now, when you took neutron and neutron, you found that there is only an attractive force. The reason is that force will always be the gravitational force. A neutron's mass is same as the mass of a proton. So this, if you study higher physics, you will find that this attractive force is same as this attractive force between two protons. But you never saw any repulsion in them because this fellow is neutral electrically. Means no charge is associated with a neutron. Is this clear? No charge is associated. So it's all about iteration. Electron, we first found there is an attraction due to gravitational force. There is a repulsion. Why is the repulsion? The repulsion is due to the electrostatic force attributed to charge, whereas the attractive force is due to the gravitational force which is attracted. Now go back to your grade 8, you studied about contact and non-contact forces, and the three non-contact forces were electrostatic, magnetic and gravitational. And you used to write a line, while gravitational is the only attractive, magnetic and electrostatic forces can either be attractive or be repulsive. Clear? Okay. If you feel that it's a little bit hot, you can switch on that fan. Okay. Okay. Is this understood now? Right. Then what we did, we could conclude that the charge value on a proton and the charge value on an electron is same. However, the nature of charge is different. Because when we took a proton and a proton, we found repulsion, electron-electron repulsion, but with a proton and an electron, we found force was same, but there was an attraction. That means the charge has to be different, right? And when we took two neutrons, what did we find? We took neutrons and we found that there is only an attractive force. There is no repulsive force, which shows that the force which is predominant between two neutrons is the gravitational force owing to their mass. And the mass of a neutron is almost same as the mass of a proton, which means the attractive force will be exactly same. Then suppose you arbitrarily consider a volume, okay? Let's say a volume. And in this volume, if you take an electron and if you take a proton, right, a sealed volume, this is a hypothetical understanding. Take a volume and fill this volume with one electron and one proton. It forms another new entity. But the stylish thing is that if there is an electron in the vicinity or a proton in the vicinity, this entity neither attracts an electron or a proton, because the electron and the proton has neutralized themselves in terms of the charges, and there is no electrical attraction. So now if this is neutral, it neither attracts this, it neither attracts this. So all milk and water now cleared, correct? So based on this, what all can we say? We can say that you have atoms, and in atoms you are having electron and you are having proton. So if we talk in terms of charge, then we will say that the magnitude is same, and that magnitude is 1.6 into 10 to the power minus 19 coulomb. Is this clear now? However, when we again talk about these two's nature of charge, the nature of charge, we say that they are opposite. That means I have to assign a mathematical relation now to clarify this subjective statement. So I say that, see, there's a difference between charge and a charged body. There's a difference between charge and a charged body. A charge is a fundamental property of matter. I am matter. You can charge me up. I become a charged body. You can charge this up. It becomes a charged body, which is the charged stylus, the charged human being. Similarly, this is a subatomic particle which is also charged. This is the smallest subatomic particle which you can, means in matter, if you want to charge at an atomic level or a subatomic level, this is the smallest level at which you are able to charge. Do you understand? Right. So nature of charge is opposite, and we say that the electron is assigned with a negative charge, right? And the proton is assigned with a positive charge. Did you understand this? And if I call both these charge, what is the charge of an electron? Okay, say charge on an electron. I say minus E. 1 minus E charge is there on an electron. Have you understood? 1 minus E. Then I would say, what is the charge on a proton? Because since the charges have the same magnitude, I will say 1 E is the charge on a proton. Did you understand? E is not electron. E is the net charge on an electron. E negative, E positive. Did we understand this thing? Okay. So if you take matter, say this is matter, then the charge that is present in a matter can be attributed to say n1 number of, it can have positive charges and it can have n2 number of say negative charges. Instead, I would write this as say, so that 1 minute children. I would write this as 1 negative E. It makes it more clear now. So the matter is attributed to two types of charges, and if you now talk what is the net charge on this matter, then I would say the net charge is always additive. It is n1 times of E added with n2 times of negative E. And if N1 is equal to N2, the matter is electrically neutral. Getting it clear now? Okay. Okay. So the universe now, what are the adopted, now we should say, the adopted understanding based on which electrostatics studies will hover on is that we have a positive charge and we have a negative charge. Now see children, I'm talking in terms of charge now. The positive charge is said as plus Q, the negative charge is said as minus Q. Can you think of a electrically charged entity to represent these two? Yes, the smallest electrical entity to represent these two would be a proton on this side and an electron on this side. Right? Understood? A proton carries, and how much amount of charge is there in a proton? The amount of charge on a proton is E. This is negative E. So now we can adjust that. If you want an absolute value, the charge with the nature and magnitude here, I would say 1.6 10 to the power minus 19 coulomb, and here the charge will be negative 1.6 into 10 to the power minus 19 coulomb. Okay. If the charges, these are proton and electron beta, if the charges, this would have been any other charge body, and if the charges would have had what you call positive signage on both, then if you bring these two bodies close to each other, there will be a repulsive force. And if you have negative charges between both, they can be equal or unequal, there will always be an attractive force between the two. Understood? So we talk about some properties of charge. You have understood this. Conductors, insulators, we have understood conductors, insulators at detail in semiconductors chapter, much more detail. Okay. So the next thing that comes up is charge is additive. Additive means if I have say Ne and I have another charge say Me, then you can actually add these two with their signages, right? It's a algebraic addition. It's an algebraic addition, and to be very easy for you, say you have got plus 5 coulomb added with negative 3 coulomb. This will give you 2 coulombs. Charge is additive, and the unit of charge is coulomb, right? And this comes from your grade 10. You knew 1 ampere current when 1 coulomb charge crosses a cross section over 1 second. So 1 coulomb is equal to 1 ampere multiplied by 1 second. Clear? Just for your knowledge, in CGS unit, we have another charge unit called stat coulomb. This is a smaller charge unit. I think 1 stat coulomb is 3.38 into 10 to the power minus 10 coulomb. Just for knowledge, there's a small unit called stat coulomb. Okay. You can create, or you can even destroy, or the other word we use is annihilate. A-N-N-I-H-I-L-A-T, annihilate. Okay. You can create or destroy a charged particle. Now you will say, sir, how is this possible? Radioactive reactions, you can create a beta particle, you can create a positron, right? You can eat up a beta particle, you can eat up an alpha particle, you can create or destroy a charged particle, but you cannot destroy net charge. Net charge, which means charge is conserved. It's a conservative property. Charge of a body is conserved. If you are beta killing charge body somewhere, this charge you have killed it because this charge must have got transferred to some other place. The overall charge is always conserved. It's just like energy. You can create or destroy a charged particle, but you cannot destroy net charge. Okay, and charge is quantized. What is quantized? Quantized means the transfer of charge, addition, deletion, transfer will always be in discrete, unique quantity. Discrete, unique quantity. What does that mean? Okay, let's understand. Atmosphere is composed of what? End of the day, electrons, and the universe has got matter. Matter is, in terms of charged particles, what are the matter? Electrons and protons. So if I want to transfer charge to you, I have to transfer some charged matter to you. So what am I transferring end of the day? Some discrete counts of protons and some counts of electrons. Neutrons are also going, they don't hamper it. Are you understanding? I cannot break an electron and give you a charge. Therefore, we say charge is quantized, means the charge will always move as plus minus Ne, where N can be 1, 2, 3, 0. So if I withdraw charge from your body, then also I'm withdrawing it in the count of E. I can give you 1, it's okay. I transferred 1 electron to you. How much charge I gave you? 1 E. I gave you 1 electron and 1 proton. How much did I give you? 0 E. 1 electron, 1 proton. I give you 2 protons and 1 electron. I give you plus 1 E overall. So the addition, the deletion, the withdrawal, everything happens in quantized. Quantized means that there is a discrete packet. Chocobar ice cream is sold in 1 units. You eat 50 chocobars, no matter. But you can't go to the shop and tell, I'm all done, I can eat 1 bite. That 1 bite your mom may give you, but the shop will not give you. They will sell you in quantized manner, which is discrete. By the way, there's a new chocobar in Blinkit, whose name is some probiotic or something. Very tasty. I just tried that. Yeah. And I love those, the Grameen sticks. Have you eaten kulfi? There's a sugarless variant also in that. And there are those circular slices that comes in that dabba, 3 or 4. Those are nice ones. And if you want to go in econo mode, then Aruns are also not bad. Yeah, Aruns are instructor. Yeah. Okay. That shop was why they went away, I don't know. That was a thing. Okay, is this much clear? Charge is quantized. So sometimes you are asked, what is the property of charge, right? A charge particle can be created and destroyed, but a net charge cannot be destroyed. Charges are additive and charge is quantized. That is, the charge always moves in discrete quantity, which is known as plus minus N, where N can take the values of 0, 1, 2, 3 onwards. Clear this much? Okay, fine. So this was all about the startup lecture about charges, and then we come to our first what do you call law, plus we should also understand that a lot of numericals are involved out here. Okay, Coulomb's law. Now Coulomb's law is analogous to the universal law of gravitation, which we have studied in grade 9. Now suppose you have 2 charges. Okay, let's say we take this charge as plus q, and I'm taking this charge also as plus q, just for the simplicity of understanding. So Coulomb's law will tell you about the electrostatic force between 2 charges which are at rest and are separated by a distance. Let's say the distance of separation between them is r. The distance of separation between them is r. So Coulomb's law says that the force, and now we will go with a little bit of adjective. So we will add, this is electrostatic force. The electrostatic force of attraction or repulsion, okay, between 2 charged bodies charged bodies is A, directly proportional to the product of their charges, directly proportional to the product of the magnitude of the charges, okay, product of the magnitude of the charges. The only thing is that if you have separate polarity out here, then it will be attractive. If you have same polarity, it will always be repulsive. Is directly proportional. This, and this also follows the inverse square law, says inversely proportional to the square of the distance between them. Inversely proportional to the square of the distance of separation. Product of magnitude of charges. The electrostatic force of attraction or repulsion between two charged bodies is directly proportional to the product of magnitude of the charges and inversely proportional to the square of the distance of separation. Square of distance of separation, right? And this force, okay, this force, there's some more interesting things that we should note out here. So what I'm doing here is that, right? So out here, what do you see, children? Out here, I see that I have got a charge, say, I have got a charge Q1 and I have got a charge Q2. I've got a charge Q1 and Q2. So it will be a repulsive force, right? And the force will always act along the line joining the two charges, right? This force, the electrostatic force, sorry, this always acts along the line joining the two charges. Acha. This was actually this what do you call, this force and all, this was proved also by Cavendish, had done all those experiments, okay. Now when you actually say that the force acts along the line joining the two charges, there are some nomenclatures that we use. Now tell me, children, don't you think that both the charged bodies will be feeling some sort of force? Yes, he will also get repelled. This is a very simple assumption. It's not like that. There are millions of charges in and around a charged body. So I'm saying that there is a charge that Q2 will feel, and there is a charge, sorry, and there, sorry. So along the line joining the two, so 1 minute, huh? Okay, we'll take away this character also. Two charges, fine. So Q2 will be feeling a charge on this side, and similarly Q1 will be feeling a charge on this side, and Q2 will be experiencing a force on this side. Now the way we name it, okay, now way we name it is something like this. I will call this as force on 1 due to 2. Force on 1 due to 2, and I will call this as force on 2 due to 1. This is read as force experienced by 1 due to 2. Right? So you know what that will say. That will say force experienced by 2 due to 1. Okay, children. Are the nature of forces same? Both are electrostatic force, two body system. Newton's third law is applicable out here. If this is the action force, this is the reaction force. Do you agree? Okay. So direction wise, we will say that an F12 in terms of vector format, we will say is always negative of what? F21. Have you understood this? This is a two body system and the forces are of same nature. So if one force, if you say that this force is my action force, then this force is my reaction force. Overall, F21 and F12, see, don't get confused here. Children get lots of confusion. F21, F12 are the forces which you are seeing individually one particle. I am Q1, there is Q2 out there. Due to Q2, what is the force on me? Right? So I call it as F12, force on me due to him. And I am Q2, there is Q1, what is the force on me? F21. After all, it is, and if you see the magnitude of the force is same, because they are action reaction forces. So if I go by magnitude, okay, so an F21, the magnitude of this vector will be same as F12. Have you understood this or not? Right. When you are talking about this and you're trying to define in electrostatics, you are actually defining this, the magnitude. Got it? So now mathematically you will write that the force, the electric force, is directly proportional to Q1 Q2 upon R square. You may ask me, sir, why are you not writing F12 or F21? Are bhai, F12 and F21 magnitude wise are same. So that is shown as the electrostatic force. You faced repulsion. What was the force? Electrostatic. You faced repulsion. What was the force? Electrostatic. So the electrostatic force is given as this, right? And when you work in terms of SI unit, then F electric, the easiest way to remember, it's given as K Q1 Q2 upon R square. And if Q1 Q2 are represented in, say, sorry, if say R square, so I say if Q1 equals to Q2 is equal to 1 coulomb and R is equal to 1 meter, and they are in vacuum. This is very important. Vacuum, or we say they are in free space. There should not be any hindrance between them. Then the value of K is taken as 9 into 10 to the power 9. Now look at K. 9 into 10 to the power 9. See, if this is 1, just see, if this is 1, 1, 1, all of them lose their, what you call, existence. So F becomes equals to K. In this case, F becomes equals to K. So you can actually say what is K. This K is small k, children. Huh? This is small k. K. If somebody tells you what is K, K is the force of attraction or repulsion between two charged entities of unit charge separated by a unit distance. F becomes equals to K, and then it will be, now take K this side, F will be always in Newton, the meter square goes this side, so it is meter square, and K is this side, so it is Newton, and the Coulomb square comes this side, so it's Coulomb minus 2. Is this understood? How do you get the value of K? There are some specific criteria. Charges must be in vacuum or in free space. If the value of the charges is equal to 1 coulomb, right? Value of the charges is equal to 1 coulomb, and the distance of separation is 1 meter, then F electric equals to K, and then the value of K is said to be 9 into 10 to the power 9. So if somebody asks you that, tell me children, if two charges of 1 coulomb are separated by a distance of 1 meter, what is the force of attraction between them? The force of attraction between them is 9 into 10 to the power 9 Newton. Very high force. 1 coulomb charge बहुत बड़ा होता है. You might feel that 1 coulomb is a very small amount of charge. It is not like that. 1 coulomb is a very big charge. In order to make 1 coulomb, how many electrons you have to give? 1 electron brings how much only? 1.6 into 10 to the power minus 19. That means 1.6, this was your first problem in grade 10. 1.6 into 10 to the power minus 19 is brought by 1 coulomb, right? 1 electron. So 1 coulomb will be brought by 1 by 1.6 into 10 to the power minus 7. So overall 6.25 into 10 to the power plus 18 or plus 19 electrons are required to bring a charge of 1 coulomb. 1 coulomb is quite a big charge. What has happened again? Okay. Just 1 minute. Charging mode, yeah. Oh, no, it had gone to charging mode and it just changes battery. Okay. Till this much is clear? Okay. Let's go a little bit more further on this K. K is taken as 9 into 10 to the power 9 Newton meter square Coulomb minus 2. Clear? The value of K is actually equal to a constant which is given by 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught, where epsilon naught is known as permittivity of free space. Permittivity of free space, and it itself takes the value 8.854 10 to the power minus 12. Now look at epsilon naught. If you take epsilon naught this side, then K comes down, right? Rest is all constant. K comes down, rest is all constant. So just swap everything of K. So it will become Newton minus 1, meter minus 2. Did you understand this? In fact, if you do this calculation, it will give you 9 into 10 to the power 9. Now we need to understand if the two charges Q1 and Q2 are not in free space but are in some medium, and that medium can be an insulator or say something called a dielectric. So let's understand what is a dielectric. A dielectric is a special kind of insulation material which does not conduct but supports electric field. Means if you place a, how to tell you, yeah, this way you understand. Both of them are learned person and we are studying civics. They are always taught you will not vote under the influence of religion, caste, gender. Both are learned. When this one is taken in an electric field, this one still retains the education. When this one is taken in the electric field, this one gets polarized. This one will vote in favor of caste, religion, gender and all. Are you understanding? Dielectrics are insulators which do not conduct but get polarized when placed in an electric field. We will study about them. That means dielectrics support electric field. इसको आप polarize कर सकते हो. We call them ना, that vote bank is very polarized. That is a religiously polarized vote bank. That is a communally polarized, or that is a gender-wise polarized vote. Means they will vote by some manifesto. Have you understood? So if you are placing them in any medium which is other than free space or vacuum, then so we say F vacuum is always given by 1 by 4 pi epsilon naught Q1 Q2 by R square. Have you understood this? This is F vacuum. And if you are putting it in a medium, then F medium will be given by 1 by 4 pi epsilon naught a capital K Q1 Q2 upon R square. Got it? This capital K, the capital K is called the dielectric constant. Don't mix it up with that small k, okay? Dielectric constant of the medium. Now children, you see a problem of electrostatics, you happily start putting 9 into k 10 to the power 9. You are given this authority only if the charges are in vacuum or free space. If the charges are not in vacuum or free space, you cannot use this equation, this k value, right? So let's get the value. Now if you do F vac upon F medium, what do you get? Okay, we get, say, 4 pi epsilon naught. So I say 1 by 4 pi epsilon naught, right? Then I have a Q1, I have a Q2, I have a R square, and now we will swap everything. I have a 4 pi epsilon naught K, I have a R square, I have a Q1, and I have a Q2. Agreed? So 4 pi epsilon naught, 4 pi epsilon naught cancels each other. R square cancels. Q1, Q2 cancels. The only fellow you are left with is K. So you say F back upon F medium is equal to K. And K is known as your dielectric constant. Now, suppose somebody asks you, define dielectric constant of a medium. Now, you should be able to define from this expression itself. Define dielectric constant of a medium. You will say the dielectric constant of a medium is the ratio of the electrostatic force between two charged particles separated by a distance when kept in vacuum to when kept in a medium without any change in the charge's magnitude, polarity, or the distance of separation. You can put in English as you like. Right. So it says the dielectric constant of a medium is the ratio of electrostatic force between two charged entities when placed in vacuum to when placed in the medium with the same distance of separation between them. I think that's the better one. It's perfect, you know, perfect. The dielectric constant of a medium is defined as the ratio of electrostatic force between two charged entities when placed in vacuum or free space to when placed in a medium with the same distance of separation between them. That means, have you written this? Bacha Party, have you written? Okay. Can I just go to the next slide? I have something more to puke. Okay. That means if I bring Coulomb's law and I now write F electric between two charged entities Q1 and Q2. As of now, see in this chapter, beta, whenever I'm writing like this, I'm writing what the magnitude of the force. Okay, please understand. Force is a vector quantity. Ideally, you should say, sir, why are you not writing like this? What is the difference? This tells me about the magnitude of the force. This will tell me the direction of the force. As of now, direction I'm not bothered because in electrostatic force of attraction, you can't have a direction. Sometimes nail, sometimes thumb, sometimes this. Okay, in electrostatic force of attraction, you can't expect somebody to go 30 degree, 40 degree between two charged entities because the force will always be between along the line joining the two. Because we are having a two charge system, we are not having many. So as of now, I'm restricting myself only to the magnitude part. Okay, so F electric between two charged particles, I would say that it is always better for me to write 1 by 4 pi epsilon naught K, capital K. K means dielectric constant multiplied by the product of Q1, Q2 upon R squared. So when the medium is air, not air, they take air also as free space only. Air is also considered as a vacuum or it's free space. At that time, K takes the value as 1. So you take the expression as F electric equal to 1 upon 4 pi epsilon naught. You write it as Q1 Q2 by R square, which you happily are being using as K Q1 Q2 by R square. But if it was some dielectric like say mica or something other, ceramic, and they tell you that the K of ceramic is so much, then at that time you don't have the freedom to go this way. You will go only this way. Is this understood? A lot of things you understood today in one go. Acha, I'm just writing. These are like my light chapters. These are the topics which are slowly going to come one after the other, right? This. So after this topic, your Coulomb's law comes to an end. And at Coulomb's law level, you have got a lot of numericals. So there is vector form of Coulomb's law, superposition. Now you tell me, do you want to do vector form of Coulomb's law today? But do you know, like people have those confusions like which side R should go, which side this should go. You want to do it? Okay, sure. So we'll do that. So Coulomb's law in vector form. Coulomb's law in vector form will be written like this: F electric vector is equal to 1 by 4 pi epsilon naught. And let's say for simplicity, the Coulomb's law in vector form is being say illustrated in free space. Okay, so I'm writing K Q1 Q2 upon, there has to be an R vector, and we will take the modulus of the R vector. The modulus means the distance, and since this is a force has to have a direction. So in order to give direction to this force, we have to give something which is known as a unit vector, which is R cap. So your whole problem in your head is out here. What is this and this and this? Okay, so first you should understand what is a unit vector. What is a unit vector? Suppose you have a vector A. You have a vector A, right? A unit vector is a vector which has direction, but the magnitude of this vector is equal to 1 unit. If it is a force, it is 1 Newton and has a direction, right? So I have a vector A. Now this vector is not a unit vector. This is not a unit vector, but I will see, somebody tells me A vector. So A as a vector must be pointing in some direction, children. Let's say this is how A vector, see, whether the vector goes this way or that way, upon the head we will always show arrow on the right hand side only. Are these things clear? Okay. Another thing I wanted to say, suppose the vector is pointing this side, you don't write the vector like this. You will still continue to write the vector A only to show the direction. Now A as a vector, let's say, has got something like, its value is, I'm showing this as a force, its value is say 5 Newton. 5 Newton. What is the magnitude of A? 5 Newton. How do you find the direction of A? You don't know whether the direction is north, south, east, west. So in mathematics, we will use something called a unit vector. The unit vector is like, yeah, have you seen those guns with the bayonet on that? The bayonet is where it is, the gun is pointing, and the magnitude is the gun. So unit vector will guide it. So unit vector means, what I'll do, I'll take the vector and I'll strip off all the magnitude out of it. Imagine 5 Newton divided by the value 5 is what? 1 Newton. Understood? Now, if you look at this vector, this is a vector in which you are multiplying a scalar value of 1 upon A magnitude. You're doing a scalar multiple. Suppose I am a vector A, you multiply 5 with me, I become how much? 5A. Now you are multiplying 1 by 5A with me. So I become how much? 1A. Has my direction changed? No. This is known as, this quantity will be known as A cap, which is the unit vector. Understood? This is known as unit vector. So if somebody tells you that there is a vector, say A is a vector whose modulus is equal to say 5, whose modulus is equal to 5. What is the unit vector of A? What is the unit vector? So A unit vector will be A vector divided by 5. This is the unit vector. Is this thing clear? R. What is R? We may not derive it, but first understand what is R. R is the distance of separation between the two charges. And what did you learn? That the force of attraction or repulsion always acts along the line joining. So I have to take an arbitrary direction of R. Let's say if my R is a vector and the arbitrary direction of R is in this side. R is it's a displacement vector, not distance. It's a displacement vector. Then tell me, R cap will point in which direction? Same direction. That is the direction the force will be taking up. This is the nutshell of Coulomb's law in vector form. Now what we will do, we will take the charge q1 and we will take the charge q2, and we will try to see, you can't have now just an F electric. Now our charges will be our forces will be either force on 1 due to 2, or we will say force on 2 due to 1. Either one force we will express in Coulomb's law, whose magnitude is same as the electric force. You want to do the derivation now? Okay, yes. Well, we'll do it next class also, but since you are interested a little bit, because what happens the next batch now, a few students they just come immediately at 6:30. The class is at 7. Okay, see how it happens. Let's say you have two charges. Okay, I will do this derivation again, don't worry. There are two charges. Let me say this charge is q1 and this charge is q2. Fine. And this is the origin of a system, so you have to have something which is known as position vectors. These are known as position vectors. Position vectors means where is the charge located in context to a Cartesian coordinate system, right? So I call this as q1's position vector is r1, q2's position vector is r2. Clear? Okay. And then I should also include something which is known as the displacement vector. One is this displacement vector. Tell me children, from where to where are you coming? 1 to 2 you are coming. So this is my displacement vector r12. You're coming from 1 to 2. Similarly, you also have the option of having the displacement from 2 to 1. Nobody stops you. This is r21. From the diagram, it is established that r12 is opposite of r21. No, sir, we don't agree with you. Okay, don't agree with me. So let's see how it happens. Let's apply triangle law of vectors. Very easy. So we'll go by r12. Okay, we'll go by r12. Keep your eyes on r12. You are starting from origin, which is r1. Then you are going by r12. Is the direction still the same? Yes. And then suddenly you obstruct with another arrow. This arrow is obstructing you. Yes or no? Minus r2. Overall should be 0. Agreed? So what is the value of r12 from here? It will be an r2 minus r1. Final minus initial. Simple mathematics. Vectors. Now let's go by r21. Start. R1, obstruction. R21, obstruction. R2 is equal to 0. Agreed? So we found R. So let's take this one that side. R21 now, if you see, is R1 minus R2. Do you agree? R12. Okay. Now multiply both sides by minus 1. This is negative R21 is equal to R2 minus R1. Now just put your eyes on these two. Are the RHS same? Yeah. Then the LHS should be same. Beyond this, we'll do in next class. Because otherwise it will be too much for you. Okay. But still, if there is time, we can understand some more thing. Okay. Whenever you see a force on 2 due to 1. Force on 2 due to 1. So when you see force on 2 due to 1, then we will take the force. Forces are all. Acha, tell me, how to find which direction is the force acting on me? Common sense. You are applying a force to me, but you have blindfolded me. No, let's make him the observer. You have blindfolded him and you are applying a force on me. And you are asking him, which direction am I applying force to, sir? He can't see, but he can ask a question. Which side did sir move? So basically he's asking, what is my displacement vector's direction? That direction should be the force. Do you agree? So since Q1 and Q2 are of same nature, look here, we'll do it again next chapter. So if Q1 and Q2 are of same nature, don't you think Q2 will face a force on this side? Q2 will face a force on this side. That will be along the displacement vector r12. And in similar lines, I would say q1 will face a force on this side, which will be the force displacement vector r21. So can I now write like this? Can I write like this, that this is the force F21, the force on 2 due to 1, acts along the vector r12, whereas this is the force 1 on due to 2 acts along the force. Right? So now you can apply your law and you can straight away write. So already proved. Why should we wait? So you write F21 is equal to K Q1 Q2, both being scalar quantities, divided by F21, child. See, oh sorry, F12. F12 means which displacement will you take? R21. So you will say R21 as a vector and the square of its magnitude multiplied by R21 cap. R21's direction is shown by what? R21 cap. And similarly, if you see F21 as a force, it would be K Q1 Q2 upon F21 will act along R12 vector, right? And it will be R12 cap. Agreed? These are magnitude, their values are same. These are magnitude, their values are same. But my child, tell me, can I not swap these two? Obviously. What is R21? R21 is a unit vector on this direction. What is R12? Unit vector on this direction. How can you swap? Put a negative. I just put a negative on this side, and I can write it as, I can now write it as, say, negative K Q1 Q2 divided by, instead of R12 I write R21, because see children, I am using only magnitude, but here now I am using the cap R21 cap. Can I write this? And is this same thing not equal to F12 vector? That is Coulomb's law in vector form. That is Coulomb's law. Coulomb's law in vector form does not mean all these proof. Coulomb's law in vector form means that when you are defining this force, how are you attributing the direction of the force? The direction of the force is attributed by the displacement vector's unit vector. The displacement which you were seeing as only the magnitude, you are now seeing it as a vector. And then you have to see which side to go. He is the torchbearer, R. And if somebody asks you, sir, what is R cap? R cap was a vector obtained by taking the R vector and stripping away all its magnitude. Class closes for